I mean, I'm really exhausted. It's your shot. Share that.
Right. I want to comment. Right. Looks like a very full room. Come on in, come on in. There's a little bit more. There's one more step left here. And this chair will be free as well. How's the room on those stairs doing? Any empty seats that you can point to? Okay, all right, great. Well, it's wonderful to see you. This chair will be open as well, so if you'd like to come in, Michelle. Yeah, right. Great. All right. Well, welcome everybody. Thanks for making your way in on this beautiful weather. It is my great pleasure to welcome Frank Wilczek to our physics club. I was explaining to him that physics club is our colloquium series. So he's here. It's a little bit of an unusual way to invite a speaker, but he's here as our collaborator for the Alpha collaboration, and I think you'll hear a little bit more about that. But I would like to introduce Frank. So he is currently the Hermann Feshbach Professor of Physics at MIT. He's the Chief Scientist of the T.D. Lee Institute and Wilczek Quantum Center at the Shanghai Jiao Tong University. He's distinguished professor at Arizona State and professor at Stockholm University. Okay, not yet a professor at Yale. Great. Okay. All right. He's made seminal contributions to fundamental particle physics, cosmology, and physics of materials. His current theoretical research includes work on axions, anyons, and time crystals. These are concepts in physics which he named and pioneered. Each has become major focus of research worldwide. And I think many of you know that he is the recipient of Nobel Prize for his work. So without further ado, I think I'll let you take it away.
Thank you. It's lovely to be here in the old building. I have a lot to say, so I think I better just get started here. So I'd like to start with a classic quotation from St. Augustine. This is in his Confessions, book 11, which is a meditation on time. St. Augustine was very much vexed by a question from one of his parishioners, which was, what was God doing before he created the universe? And Augustine's immediate response was preparing hell for people who ask such questions. But the question stuck with him, and he thought very hard about it and came up with an answer that's very interesting to this day, which is that time is what clocks measure, and before creation there were no clocks, so there was no time, and the question dissolves. We have the spirit of that answer still survives today at the frontiers of our understanding, But I'd like to make it a little more precise. Time is the t that appears in d by dt. That is in our formulation of the fundamental laws of how the world works. There's something called t. There's a variable called t that tells us how things change. And it's the same for everybody. Everybody uses the same t. And it's how that marches along that defines our perception of time and really what time is. But that's kind of abstract. We'd like to say something about its character. And I think the most profound thing we've learned about time is that it's something we can consider as an extra dimension, in a sense, in addition to the dimensions of space, and that it has, like space, symmetries. It has two characteristic symmetries, at least on small scales. Cosmologically, there are other issues, which we'll somewhat address here. But the two symmetries of time and fundamental law that are very worth considering, and also in applications, are t, that is time reversal, and tau, which is time translation symmetry. Time translation symmetry doesn't have a universally recognized conventional symbol, so I've just invented one, tau. So let's first discuss time reversal. And from my perspective, now I hope becoming widely shared, this is the story of the road to axions. So the laws of physics are very nearly symmetric under time reversal, but the physical world is not. This raises two questions. Well, first of all, the world is not in many ways. There's a cosmological arrow. The Big Bang is in the past. Something else is in the future. Radiation goes out, but not in, typically. The thermodynamic arrow of time, which J. Willard Gibbs made great use of, the second law of thermodynamics. Psychological time, we remember more or less the past and only guess and plan for the future, and they're very different. So all this raises two questions, one of which is rarely asked, but would not have been fruitful to ask, perhaps, before the last 50 years, but now is very much a question. Why do the laws have this symmetry, this time reversal symmetry, which is not only not necessary to describe the macroscopic world, but a big embarrassment? Because the world doesn't look that way. And that's the second question. Why does the world violate it in many ways? So present day science has impressive partial answers for both questions. Question two, I'd say, is more mature and more secure in our understanding. That is, there's a convincing, although not universally agreed story, that shows that the many arrows of time, the psychological, radiative, thermodynamic, and so forth, all follow from one, namely the strange but simple asymmetry of the Big Bang. This is an iconic picture of the microwave background radiation, the microwave sky, with its contrast dialed up by 10 to the fourth. So the fact that you can see asymmetries only if you dial it up by 10 to the fourth means that the matter at that time was, in the early history, was very uniformly distributed, and that makes matter happy. That's the most probable distribution. That's equilibrium. But gravity is very unhappy. Gravity would like things to clump. This is, well, follows from the equations of gravity, but it also appears, for instance, notably in the fact that if you calculate the entropy of black holes, it's enormously large. So you gain a lot of entropy by having things clump and making gravity happy. But the universe didn't do that. And the subsequent history of the universe is a long twilight struggle of gravity to get satisfied, to make things clump. And along the way, things clump, nuclear energy gets released, stars, life, all the other things we mentioned that are the macroscopic appearance of time reversal violation, I believe, follow from this. For question 1, regarding the fact that the laws do approximately, very nearly obey T-symmetry, there's a convincing story that almost derives it from deeper sacred principles. This was the achievement especially of these gentlemen, Kobayashi and Masukawa, who got the Nobel Prize for their analysis. They showed that within the context of the Standard Model and its description of matter based on quantum field theory, which means the embodiment of quantum mechanics, special relativity, well, and general relativity too, and gauge symmetry, that the time reversal symmetry of the laws follows as a kind of accidental consequence of those presumably deeper principles. But fortunately for them, they made a mistake, or they didn't realize that their derivation was incomplete. There's another, so they thought that there was only one potential kind of T violation in the Standard Model that was adequate to parameterize the observed T violation if you had a third family of quarks and leptons, which was duly discovered, and then many other consequences of their idea were verified. And so the Swedish Academy was not wrong to reward them. But there's another potential T violating interaction that is also allowed by all the general principles, but doesn't happen. The numerical measure of the strength of this interaction, which is something called the theta term in quantum chromodynamics, is that it's equal to or less than 10 to the minus 10th. Okay? The observed phenomena that puts a very powerful limit on this is the fact that the neutron has a very, very small, well, never yet detected electric dipole moment. So, is that a coincidence? Let's hope not. Such a striking quantitative phenomenon deserves a qualitative explanation. And over the past 40 plus years now, there have been many attempts to explain it, but only one has stood the test of time and time reversal. And this is something, this has as a consequence the existence of a new kind of particle that I named the axion. And I, in fact, named it after this laundry detergent. Before, a few years before the naming, I had been shopping at a supermarket with my mother and saw this detergent on the shelf and said, if I ever get a chance to name a particle, this would be a strong candidate because it's Greek, it's kind of sounds very strong. And it turned out that a few years later, it was about 3 years later, there was a problem with an axial current, the conservation of axial baryon number. And so I was able to tell the editors of Physical Review Letters that I was naming it not after a laundry detergent, but after its role in physical law, and that was acceptable. Anyway, so this axion is a spin zero particle whose properties are connected very closely with the job it needs to do, so we can say a lot about it. But I'm not going to give any formal derivations here. I just want to an indication of the nature of the theory and its profound nature, and also how it leads to a spectacular, unexpected consequence. In addition to solving that issue of T violation, sort of dotting the I's and crossing the T's on T violation, it also may be most of the universe. So to solve this issue of the extra parameter that you don't want, the most popular, really the only successful idea, is to have a theory of evolution. What appears within the standard model as a coupling constant, so just a constant of nature that never changes, instead becomes a dynamical variable in this theory. And if you set the theory upright, which is not difficult to do, you have to add a little bit of symmetry and an extra complex scalar field to the standard model, then you find that this field has its energy minimum at a place that restores T violation as well as it can. So it makes this so-called coincidence that the T violation, this potential extra source of T violation, goes away into a consequence of dynamics and symmetry. Now, it's very difficult. If you add things to the standard model, or if you add things to quantum field theory, add dynamical variables, they're fields. So they fill all space, and their fields create and destroy particles. But fields are difficult to draw. So in this picture, I've taken one point. You have to imagine this is going on everywhere in space. I've taken one point and drawn the internal space. That is, it's a complex field, so it has both a real and imaginary part, and the energy density associated with it is connected with the value of that field. So it makes this kind of Mexican hat structure, and the magnitude is called the condensate, and the phase is the axion. The condensate is a massive field because you have oscillations around the absolute value of the field, but it also has a much shallower direction, which has oscillations that creates very light particles, and those are the axions. So the new field relaxes towards a T-symmetric energy minimum, and you can follow out the equations of cosmology to see whether this proposed dynamical mechanism actually works. At first, people said, let's just minimize the energy, and they were happy. You minimize the energy, and the only stable point is the symmetric point. So that was good. However, in the mid-70s, particle physicists were learning to take cosmology seriously, for better or worse. So we wanted to see if this actually happened in the Big Bang for generic initial conditions. And when we did, there was an extraordinary bonus. We found that this particle, which interacts very, very feebly with ordinary matter, also gets produced a lot in the early universe, and in fact, has all the right properties to be the dark matter that astronomers need to explain things like the gravitational bending of light that you see here, which quantitatively can't be accounted for by the ordinary matter between you and the images. It needs about 6 times more than you can account for that way. So you see these streaks, you also see multiple images. Those are the same thing, actually, bent over and over again. And there's now many, many different ways in which the dark matter has been detected, and it fits very well with the idea that you have production of a new kind of particle in the early universe. It's no extra parameters. It comes for free with the solution of this problem in fundamental physics. This naturally has attracted a lot of attention, and people have constrained the parameters. I should say it's basically a one-parameter theory, and you see this golden band here that displays an aspect of that one-parameterness. This is a plot of the mass of the axion, by the way, which is very light by particle physics standards, but not zero. And it's coupling to photons, which is very, very small. And this is the golden line with some theoretical uncertainties in models. The nice model is this top one, but there are also a lot of less nice models that people play with. And then it's QCD, so it's hard to do precise calculations. Anyway, this is what you have to shoot for. And people have tried all kinds of things to try to access whether this particle with its virtues, it actually exists. And you can calculate the density of axions, the density of axions that gets produced in the early universe as a function of this same parameter. And in this band here, you get the dark matter density. So we want to have experiments. Well, we want to have experiments which probe all this possible space, but we especially want experiments which get that overlap region. And here's how you do it. A little bit simplified. Part of the theory of axions is that they couple to electromagnetic fields, and it's in a very specific way. It's very much like the way neutral pions couple to electromagnetic fields, not coincidentally, they mix with each other. But the axion couples to E dot B at the level of a local Lagrangian. So it couples to two photons in the language of particle physics, or in a mixed language where you do some fields and some particles. If you supply a background magnetic field, the axion can convert into a photon. And photons, we know how to detect. You can look at them, so to speak, if you have the right kind of eyeball. Now, the thing that has made this challenging is that the coupling is predicted to be, and consistent with experiment, is very, very small. Nobody's detected it, and that's okay. It's consistent with the theory. To encourage the axion to convert into photons, what you can do is not try to convert in empty space or space just filled with a magnetic field, but produce resonance structures that encourage the photon, that encourage the axion to couple to the photon. And that's now been the object of a lot of creativity to try to create efficient resonators, efficient converters. It's the same kind of creativity that went into designing radio receivers based on Maxwell's equations. At one time, people didn't know how to do that. Okay, they had to design things based on the equations to pick up the predicted signals, and we have a similar thing here with difference in detail. The coupling is somewhat different, and the strength is especially different, but it's the same kind of challenge, and we've been trying to rise to the challenge. And here today, we've heard a lot of the progress on it, and funding agencies are impressed. So we're proceeding. So because the signal is weak, and as you can gather from that diagram, it's proportional to the magnetic field in amplitude, so squared in the magnetic. There's a high premium on making big magnetic fields. So a big magnet is necessary together with the resonator to get a detectable signal. This is a magnet which we hope to use eventually, but this would be a 16 Tesla giant magnet. You can see the people here, but it's still in Germany. It's on its way over to the States, I understand, and eventually we hope to use it. In the meantime, we have a magnet here at Wright Lab, which is already going to make a big, big jump in our ability to detect axions. And then the third element is the eyeball. These are really microwaves that we want to look at. So the eyeball is not an eye. It's a sensor that we want to make ultra sensitive, ultra low noise. All this is driven by the fact that the predicted signal is so small, and a lot of brilliant quantum technology is going into these kinds of designs. And this is our estimate of the Alpha project, which is going to be at Yale. It's being discussed, and we know where it's going to be in the Wright Lab. Where this is, I hope, a conservative estimate of what we can achieve. We're sort of using the known techniques, and we're still pushing ahead on better technologies for the sensors and the resonators. So, and this orange band is what I showed you before. That's the sweet spot where it makes the dark matter. Okay. So we'll cover that frequency range, and the upper line here is the nice axion models. So we have a little bit of a safety factor, but we'd still like to really, in view of the many cosmological uncertainties and even uncertainties in calculations of QCD, we'd like to make sure that we keep pushing lower and broader until we find it. So this is going to happen at Wright Laboratory. And I was very encouraged to see that Wright Laboratory already advertises it as itself as a portal to the universe. There's the portal. and it's going to be transformed. That's I have to say that this picture looks like a transformed version of what I saw on the ground, but in the future, it's going to be a quite beautiful structure, and this will all be internal. So that's the story of fundamental T violation and how it leads us to axions, and a very novel and compelling, I think, theory that brings in evolutionary ideas to physics and has provided very entertaining challenges to experimentalists. And we'll see whether it proves out. Now I'd like to put this in a broader perspective of T violation, not in necessarily the fundamental laws, but in materials where there are also new ideas. First of all, what are T violation effects in matter? And of course, many things can violate time reversal in matter, but the most characteristic thing, and the thing I want to emphasize, is that if you have a correlation of moments, a correlation of magnetic moments and electric moments, so electric dipole density and a magnetic dipole density that has a preferred direction, that violates time reversal, because under time reversal, the magnetic one flips, but the electric one doesn't. So in general, magnetoelectricity involves time reversal violation. And there are many detailed experiments you can do to see whether a given material, maybe something you don't understand and have only a little bit of it, whether it violates time reversal. And this is a thriving field with many technical applications. And what I want to emphasize here is that axions and axion ideas are feeding into the ideas of T violation in matter. The coupling which I show you, the A E dot B, if you write it in terms of fields, actually it's in the presence of a magnetic field, a time varying axion field produces a current in Maxwell's equations. That's how the equations work. So you have fields becoming currents and vice versa. You have current field mixing. And that's something that's very characteristic, leads to characteristic phenomenology that can occur also in other contexts in materials. So in particular, in appropriate superconducting materials which are under study, you can have the effect that if you have a vortex, which has automatically a magnetic field, it will have a current running along it necessarily. And that might be useful in any case. It's certainly entertaining. And then I want to talk about a little, a new direction in a grand tradition. That's violation of time reversal in the biological world. Now, the grand tradition is that in the biological world, not time reversal, but its cousin, parity violation, has a glorious tradition, glorious history, going back to Pasteur in the 19th century, long before, may I mention, long before the discovery of parity violation in fundamental laws of physics. Okay. And this was very sophisticated work already in the 19th century. The key tool that Pasteur used in seeing this was optical activity. So that's the effect that if you have polarized light shining through a solution of a parity violating material, let's talk about the liquid state for purity, then if the plane of rotation rotates, that's called optical activity. And if you think about it, you'll see that that's a parity violating effect. Pasteur was a physical chemist to begin with, not a biologist at all. He wasn't trained in biology. And the puzzle he was trying to solve was there were two forms of material from different sources that seemed to be chemically identical, but one of them was optically active and the other was not. And these were, well, in a modern interpretation, they were both tartaric acid, but tartaric acid comes in two types. If you looked at what he discovered, first by looking at these samples and crystallizing them, was that the ones that were not optically active had mixtures of two types of crystals. Okay, when you took them out of solution into a crystal, whereas the ones that were optically active had only one kind. And then he investigated this very assiduously and very actively and found that the materials that were optically active and had only one form of the crystal were the things that came from living beings. So this showed that biology had a preferred orientation. Now we understand this at a molecular level. Any reasonably complicated biological molecule, but in particular amino acids, which are the building blocks of proteins and have this kind of structure, an amino group, the NH2, hydrogen, COOH, I guess that's a carboxyl group, and the carboxyl, anyway, whatever it is, and then something else that's not any of those, then it can be put together in two different ways with a carbon of valency 4. Those can be associated with hands, and that's the origin of the chirality of proteins. And it turns out all the and it can be understood at a molecular level because all the amino acids other than glycine is the one with R, is just hydrogen, nothing, only one that's used in the biological world, and it's the one that derives from this particular precursor, which is already chiral. So this precursor sets the tone for all the rest. So it's a theory of evolution before the theory of evolution in biology that, but the theory of evolution shows why you have only this one chirality, a preferred chirality. It's passed from generation to generation in the form of templates that govern early development, so it doesn't have to be relearned over and over again, and it's also very difficult to escape from. And although parity is weakly violated in fundamental law, no one has, as discovered in 1956 by Li and Yang and Madame Wu, no one has made a convincing connection between that small effect and biological chirality, and it seems far-fetched just because the fundamental parity violation is so small. However, there are still very interesting questions about the basic nature of parity violation in life. In particular, I think something that's under active investigation is the hypothesis that parity violation does have a physical origin, which is that life began in an environment that was parity breaking, could be a magnetic substrate, for instance, and that favored certain reaction pathways because of physics, certain reaction pathways as opposed to others. And this is a testable hypothesis because we can see the overall choice of one class of parity molecules versus another can't be determined a priori, but the fact that there are classes of related molecules that talk to each other in a coherent way that's favored by physical law, that's testable and reasonable. And the question is only how tight the correlations between different sets of reactions are, I think. Anyway, so I've tried to isolate questions throughout this talk. So here's the question: how did the parity asymmetry of life emerge? Can we shed light on it by this kind of consideration? And can the pattern, in particular, can the pattern of choices be deduced from physics and chemistry? Now, I promised you would talk about time, and I've been talking about parity all this time as an inspiration. Let's go back to time reversal. Biology manifestly breaks time reversal symmetry in very big ways. And as you get older, you more and more notice that time is not reversible. And development, aging, evolution, learning, many of the most basic concepts of biology are time reversal asymmetric. Most or all of this T violation can be traced to entropy and energy gradients, and then ultimately to the fact that the sun's radiation is coming to us and not going away. Okay, so I believe this is very similar to how the Big Bang sets the direction of time reversal for other things, and in biology, it's set by the sun's radiance. I don't think the Big Bang has much to do with it, other than the fact that it produced the sun as a result of gravity trying to enforce its equilibrium. Okay, much less obvious, but I think very, very interesting and possibly profound and fruitful is the role, if any, of non-dissipative T violating at non-dissipative T violation at the molecular level. And it came as a bit of a surprise to me, but it's a remarkable fact that it can be useful, and it happens. Specifically, it can be very handy to have labeled compass needles for magnetic sensing. So, for instance, if you are a tiny, dumb bacterium that would like to be at different times in different regions of the ocean. So you have the ocean has layers with different amounts of oxygen. So you might want to gather energy going up to get to the sun or to get sources of food, and then come back to the non-oxygen places where these bacteria are more comfortable, or they just might get disturbed and have to find their way home. They don't want to just diffuse randomly. And down in the ocean, there aren't a lot of signals to pick up on. But one signal is the magnetic field. And the magnetic field allows you to get a sense of which way is up and which way is down and follow magnetic field lines. And look at that. These guys make themselves into magnets. They collect the Fe3O4 magnetite, and they are better, apparently, than industrial processes at making pure little magnets and aligning them in like that. And so they use these magnets to navigate, not by reading them. They're not that smart. They are the magnets, and so they align themselves along the lines. Just move the only way they knew how to move, and that works. And this is an example of what I mentioned before as a paradigm of T violation. It's a labeled magnetic moment, so it's correlated with electrical information that tells you which way is north. So you have T violation. Okay, so that's curious and very interesting and very important to these bacteria, which are a very successful species. Well, many species, in fact. They are among the most primitive forms of life known, according to genomics. But the question arises, is that just a one-off trick, or can it be more widespread and useful? And I think there's a potentially profound use of this kind of correlation between electric and magnetic moments and T violation. That is because it can be used to transfer information between charge world and spin world. You transfer the electric dipole moment was pointing this way. You use it to align a magnetic dipole, which you put away. This is exactly what you do in computers when you want to store information. You store the information in spins, which are difficult to disturb, but also not so convenient to process. And you do the processing on the electric part, but if you want to memorize something for a while, you put it into spins and then read it out later. So very interesting questions, I think, arise. Therefore, do the remarkable magnetic skills of magnetotactic bacteria percolate up the tree of life? And in particular, is the transfer of information between charge world and spin world a significant theme in deep biology? I'd be very disappointed if it isn't. We'll see. So that's the story. That's what I wanted to say today about time reversal symmetry. Now let me move on to time translation symmetry, where some of the same themes arise, but with variations. So the fundamental laws of physics, just as in the case of time reversal symmetry, so for time translation symmetry, they are very nearly symmetric under time translation, but the physical world is not. Time translation, of course, is kind of highfalutin terminology. What it means is that the laws don't change. So the whole concept of eternal laws, of reproducible experience, reproducible experiments, all of that is tied up with time translation symmetry. There's very, very strong evidence for this symmetry. We can look back at the early universe to see if the laws have changed. And in particular, we can examine very complex spectra to see if the laws, as reflected in the spectra, operated in the same way back when this light from a distant galaxies started out towards us. And by gosh, once you correct for the redshift, they do. So the constants haven't changed very much. Nowadays, you can also measure properties of atoms encapsulated in atomic clocks, so energy splittings of atoms, so accurately that different kinds of clocks can be compared, and they don't fall out. If you compare the rate at which they're falling out of synchronization, it's less now than 1 second in the lifetime of the universe. Even though these clocks might be built of different materials based on different principles, everybody keeps the same time. So this shows that the laws don't change, so that there is a concept of time, and also that the laws aren't changing very rapidly, because if they did, the different kinds of clocks would fall out of synchronization. And it turns out that these limits are comparable to the astronomical limits. Another kind of evidence for the time translation invariance of physical laws, thanks to Emmy Noether, is the conservation of energy. Symmetries are associated with conservation laws, and the conservation law that's associated with time translation symmetry is conservation of energy. To me, conservation of energy would otherwise be extremely mysterious. You may remember the history of how you learned the conservation of energy. You start off with energy. Energy is a measure of the vigor of motion. That's kinetic energy. And turns out that's not conserved. So you add potential energy, but what is potential? Well, there's electrical potential energy, but then you learn that there are other kinds of potential energy. And then you learn that there's heat energy. And every time a new domain of physics is explored, you add radiation energy, you add more and more energy. Why? What is going on here? Well, the thing that rationalizes it is this connection between energy and symmetry, and the fact that we've been able to maintain conservation of energy is a reflection of the fact that the underlying laws are time translation symmetric. And as far as we know, that's exact, not unlike time reversal. Oh, questions? Why do the laws have this symmetry? And why does the world violate it? The same kinds of questions we had for time reversal symmetry. Or does it? See why I wonder whether it does at all in a moment. So the people who are most famous or notorious for discussing this question are David Hume, shown on the left, and Immanuel Kant, shown on the right here. Hume famously said that we have no reason to believe that the way things will behave tomorrow are the same way is the same as they're behaving today. No amount of empirical evidence can make that connection. Fair enough. Kant answered that the world would be incomprehensible, and the way we think about the world imposes that structure. I think Kant's answer is profoundly silly. And the answer, and this is a case where Tao just seems to be rock bottom. We don't know. I don't even know what it would mean to have a more profound principle that replaces it. Maybe that will appear someday, but at present there's not another layer. So it's different from time reversal symmetry in that way. Okay, but I do think that Kant gave a very silly answer. What about the fact that the universe doesn't look that way? Well, that's again a consequence of the fact that the Big Bang occurred in the past, not in the future. By the way, if there was a big, you might ask, if there was a big crunch, could that be time reversal symmetric? But it's not at all. If there's going to be a big crunch, things will clump along the way. They've already clumped to a certain extent. They'll clump even more. So if there's a big crunch, it won't look like the Big Bang at all. It'll look like a whole bunch of black holes merging, not like the cosmic microwave background radiation, unless something very, very peculiar happens. Anyway, so this same fact, the strange initial conditions of the Big Bang also violate time reversal, time translation symmetry. But they pose the question, why? If the fundamental laws do have that symmetry, why doesn't the Big Bang? You can wrap all these different versions of time translation violation into one big question, but then you have to answer that question. Maybe. Okay, so let's step back from those heady heights and talk about material Tau violation. And I don't have a lot of time, so I'll just have to say that this is what time crystals are all about. And there's a beautiful review paper that just appeared in Views of Modern Physics that I helped participate in, where you can find these complicated diagrams explaining different phases of matter that are appropriately described as spontaneous violation of time translation symmetry, time crystal. I won't attempt to explain time crystals in any meaningful detail, but I do want to say something about what they are and what their future is. So the idea that you have spontaneous breaking of a symmetry comes with several important consequences. There can be sharp phase transitions when the symmetry is restored or broken. There is rigidity against a large class of perturbations. So let's think about a magnet, just an ordinary ferromagnet, which is the paradigm of spontaneous symmetry breaking. The reason it happens is that the magnet becomes magnetic and then loses its magnetism at high temperature, is that the spins want to align in the same direction, but they don't know which direction. Now, if there are enough spins that participate, they make a collective choice. And if the material is big, there's enough collectivity, enough enforcement of that choice that everybody has to align the same on a whole macroscopic scale. And if that's the case, once you have that, local perturbations can't undo it because the structure goes off to infinity. Of course, you can always melt the material. Or you can throw it into a black hole, then it won't be a magnet anymore. But local restrained perturbations leave it the same. On the other hand, it's very sensitive to global perturbations that tend to restore the symmetry. This is the lesson of the compass, which is the epitome of spontaneous symmetry breaking. You take a compass, such as this ancient Chinese spoon, which was used as a compass. It's nice because it can rotate easily. It wouldn't be useful if it weren't robust against all kinds of local perturbations. It stays a magnet, the magnetization stays aligned if you don't do crazy things to it. And yet, it responds to a global perturbation which wants to restore the symmetry of the different directions of spins by rotating as a whole. That's why it makes a useful compass. So that's the epitome of spontaneous symmetry breaking. And we can ask, what would an object that does this for time translation symmetry look like? And for time crystals, the fact that you break time translation symmetry means that the symmetry restoring interactions are AC signals of appropriate kinds. And so time crystals will give you sensitivity, ways of making materials, and this is their signature, materials that are sensitive to specific classes of AC signals. Okay, finally, I think I should be closing soon. Yes, good. In a talk about time, I think I should respect time. So I'd like to close by talking about philosophical time, Tao, which will also relate to this question of whether Tao is broken at all. Maybe answering finally this Hume-Kant discussion, or an even more ancient philosophical discussion, which I'll show you. So way back in the 6th century BC, there was a great debate between Parmenides and Heraclitus, the two pre-Socratic philosophers. Parmenides was the philosopher of eternity. He said that despite appearances, nothing ever changes. Difficult case to make, but he did his best. And he inspired Zeno with his paradoxes. And so they made a lot of, which also showed that nothing could ever move despite appearances. And okay, he introduced a lot of confusion that people have had fun with, but okay. So our senses are unreliable. Okay. Heraclitus said that everything is in flux. And on the contrary, the senses are reliable. Who's right? Well, there's a physics analog of this debate. Well, it's not even a debate, it's different ways of describing situations that the descriptions can look very different even though the situation is the same. In fluid mechanics, we have two kinds of descriptions that go by the name Eulerian and Lagrangian, from, of course, Euler and Lagrange, but this is not, they were versatile guys, and this was different from what you usually think of as Euler's equation. Well, there are many Euler's equations, but this is a very specific thing. It's the description of fluids based on looking at velocities as a function of position and time. Okay, so you look at the velocity fields as a function of time. The Lagrangian description is you look at how the particles are moving. So you don't stay at the same place and see what the velocity, but you go with the velocity. And they can look quite different. And in fact, the interior Lagrangian flow can be rich and complex, even in situations where the exterior Euler flow is simple or even stationary. You can have an Euler flow which doesn't change at all, but the particles move around in complex ways, even chaotic ways. In quantum theory, although this doesn't seem to have been studied much, there's an analogous situation. We have currents of probability that describe flows. In fact, they describe the kinds of flows that it's me walking across the room. The flow of probability in a wave function. So they describe the experience of participants in the wave function. And that experience can be very complex, even if the wave function is not changing in time, because it's the Lagrangian description as opposed to the Euler description. So a question that I'm currently investigating is, can such flows support universal computation within a stationary wave function? And I'm very optimistic that they can. But then the second question, more obscure at present, is whether that can happen with realistic dynamics. So it seems to be kinematically allowed. Whether it's dynamically plausible remains to be seen. So with that, let me return. Oh, so Euler is like Parmenides and Lagrange is like Heraclitus. Let me return to St. Augustine then, and his question: what is time? If no one asks me, I know what it is. If I wish to explain to him who asks, I do not know. And we're still working on it, St. Augustine. Thank you for the question and all the entertainment that it's led to. Thank you. Okay, thank you.
Okay, we'll take a few questions from the audience. For those of you on Zoom or in the overflow room, do raise your hand if you have questions. And normally I would walk around the room, but today that's not going to happen. So I'll try to repeat the questions, or perhaps Frank can. I think we.
Okay.
Can
Well,
you repeat the question?
The question was whether I could expand on the concept of an anapole moment and the P and T violation in matter. And the answer is yes. I can expand. Let me do that very briefly. I mean, there's a lot to say, but it gets technical. It gets pretty technical very fast. Let me just explain what an anapole moment is. It's very interesting. It's an internal structure of fields. When you have in electromagnetism or other contexts a multipole expansion, that describes the solutions of typically Laplace's equations or some version of Laplace's equations, the Maxwell equations, outside a given region. And you allow singularities at the region. Okay, but it doesn't really tell you about possible internal fields that don't leave an external trace. And one of the fascinating things that can occur in systems that violate time reversal and parity symmetry is that you have internal moments, a so-called anapole moment, that that doesn't leave any external trace. In first order, it could lead to second order effects, but no first order, no direct effect. And these are being very actively investigated. They are in more detail in the case, for instance, in the context of superconductivity, where this is particularly interesting, an aspect of current field mixing, because if you have a superconductor and it wants to screen a magnetic field, you produce, so you have a magnetic field this way and an azimuthal current that screens the magnetic field and keeps it from invading the bulk of the superconductor. But if you have current field mixing, which you have when you have interactions that violate parity, then you get components of the current which run along the magnetic field. And that's very interesting. Another thing I should say is that there's a deep connection between this kind of possibility and the equations of axions. If you take, there are many, there's a whole field of condensed matter physics, a cottage industry of finding emergent axions. So it's things that obey the same equations as axions, of course, with very different values of the parameters, and the fields only exist within materials, suitable materials that have, but there are quasi-particles, there are degrees of freedom that are described by those equations. And if you take those fields and have simple behavior of those emergent fields, you get all these effects. And among the rest, this is the effective theory of topological insulators, which have become very fashionable. Yeah. Okay, so there's much more to say about it, but it's a seminar as opposed to colloquium. Yeah. So.
Professor Wilczek,
Yeah.
can you elaborate on what's the connection between quantum probability flow and doing computation with it? So I remember you talking about doing universal computation.
Let me give a metaphor or an example. One of the ways that is being widely discussed to do quantum computation or universal computation is using anyons. And in that context, you have motions of things, particles that as they move, they change the wave function. And the information about their flows can be a way of processing wave functions that does computation in effect. So that or a better way to put no, a simpler, much simpler and better way to put it is going back to the Incas. The Incas had something called quipu. So spelled Q-U-I-P-U. So they had invented quantum IPUs. No, it just happens to be that was a technology for storing and transmitting information based on having knots in strings. So they had these strands, they kept knots in them, and a certain pattern of knots would represent a number or a letter, and then they could transmit messages this way. And that shows you that you can have information in the form not only of zeros and ones, but of patterns of knots. In fact, it's a much richer way of storing than zeros and ones. And that's what you need here. Patterns of knots or zeros and ones that change in time is a way of having information and changing it in systematic ways. Yeah.
Hey, so from the little I've seen on time crystals and seeing them experimentally, I've seen it in the context of spontaneous breaking of a discrete time translation. Any ideas on the potential of a continuous time translation breaking? And if so, are there any idea on what like Goldstone mode would be in that instance?
Yes, I think it's actually that goes. I think the AC Josephson effect is a pretty good example of a time crystal. People object to it because when you close the circuit, there's a battery, and so there's some dissipation, and it doesn't last forever. But it can last a very, very long time, and it's constant, and you have a constant situation, but a variable response. The current goes back and forth very, very accurately for many, many cycles. And it responds sensitively to microwave radiation at the same frequency. These are things like Shapiro steps. So it's a way of describing those phenomena that doesn't introduce anything that people hadn't discovered otherwise, but maybe is conceptually pleasing and capable of generalization in different ways. So Yes.
Okay.
Yeah.
Okay, one last question.
So you mentioned how you're using these giant magnets to kind of study axions by looking at light emitted.
Yeah.
But I mean, the universe is kind of filled with giant magnets like pulsars, for
Yes.
example, right?
Yes.
Is there a reason why you're not studying like pulsar spectra for traces of axions?
Well, people are, in
Okay,
fact.
okay.
The people have.
Sorry. Okay. You mentioned you're building them here, so I didn't know if there was a reason that it's not.
Well, pulsars are complex objects, and they can give meaningful bounds, but they don't appear to be as powerful as focused experiments. And also, but people are looking for what they don't have a uniform magnetic field, and in detail, but their magnetic fields don't vary very rapidly. So in detail, when you look at the equations of axion physics, it's gradients in space and time that interact significantly. And in the context of neutron stars, those gradients are not really under control, and they're at very long wavelengths. Nevertheless, you do have strong magnetic fields, and people have attempted to put bounds on axions based on that. So you would look for emission from pulsars of radiation at a very specific frequency, the axion mass, effectively. People have actually employed the data from SETI searches to look for the people. SETI has gone out and been looking for weird radio signals. And so it's put some meaningful constraints on axion parameters, but it doesn't seem to be competitive with controlled experiments.
With that, well, let's
at least not yet. I'm told there's going to be a new array of radio telescopes. What's the name of it? I forget.
That's KCA, the square kilometer.
Square kilometer, SKA, the square kilometer array. When that comes up, it will be able to discover axions perhaps in a different range, different part of the golden band than we're looking for in the alpha collaboration, but it's conceivable now.
okay. Well, I think in the interest of time, let's thank
Good
this.
question. Very
Yes, good question. Let's thank Frank again.
Okay. Yeah.
I don't really know a lot about this, but what are your thoughts on them? And then, like, do they violate any symmetries?
Oh, those would be global objects.
Yeah.